analysis tools, I guess.
All right. So my slides are all new because I couldn't keep my mouth shut, and so I was volunteered to give this talk.
Thank you, Ben.
I want to focus on to try to answer or address three questions. What is in a root tree from the D reaction, and how can we access the data in the root tree, and as a consequence of that, how we analyze the root tree. Documentation that kind of addresses his question a little bit. There is not yet that much documentation. That's one of the reasons I can't keep my mouth shut, because I always complain about it, that we do not have enough documentation. In particular, I would say comments in your code is not enough. And I put here two links. We have a document. I started a documentation called dselector.doc as a PDF file. It's on the GitHub, but it's also on overleafs. These are links. You can actually click on them and get to the overleaf link of this documentation. And any additional information that you think is should be in this documentation, write it in. If you have this link, you can add text to the document. It's a text file or LaTeX file. So now coming, yes. So please, if you know something nobody else knows, or you think everybody else should know, write it in here. Okay, so I give you an example of one of these root trees that come out of the D reaction. And the example is pi plus, pi minus, pi zero, and proton, where the pi zero decays into the gamma gamma, but that is not defined as Alex was pointing out. You don't need to do that if you don't want, but it has some consequences, which we will come to later. And then when you look at the entries in this tree, then you see a run number, event number, trigger bits. These are values that are event specific. Each event has that. And then you have number of beam photons that are related to this event. And then the beam PID, beam X measured, beam momentum measured. Those are arrays, and the array is as big as the number here indicates. And then you have also a whole list of neutral particles for each event. It's an array, and the length of the array is defined by the number of by this value called num neutral hypos. And then, of course, there are also charged particles, and again, you have a number that indicates how many number of charged particles you have for each event, and then the data that are related to these charged particles as arrays to it. And then with the neutral particles, the charged particles, and the beam photons, you can create combinations that then make up this reaction, pi plus, pi minus, pi zero proton, or whatever reaction you have defined. And these combos are the final state particles plus one beam photon. Right? There can obviously as many combos as there are beam photons in minimum. You have additional unused tracks that you specify in the reaction, as Alex pointed out, and also unused energy. That, in other words, photons or neutral particles that have not been used to make a combo. And you can also have intermediate states, like where is it? It should be somewhere. Decaying pi zero. And that is the intermediate state that then decays into two photons. And if the mass was constrained in the kinematic fit, you will have such a name somewhere, decaying pi zero or decaying lambda, right? But the point is, if you have something like that, that means the mass was constrained, which has some consequences which I will come to later on. And that means when you look at these lists, you find variables which have a measured in the end and others which have a kin fit in the end. If they're measured, that means these are the measured quantities. Whereas the kin fit means these are the kinematic fit results from the combo. So you will have as many kin fit variables as you have combos. Whereas measured, you only have as many neutral or charged particles that are given for a given event. Does that make sense? So for example, in this reaction, I could have 10 positive charged particles, 10 negative charged particles, and 10 photons. But I only need two positives, one negative, and two gammas to look for this reaction, right? And that means, of course, I have many combos. Actually, I think at that point, the code would probably say, screw that, I'm not doing it, right? There are too many combos. All right, so.
But Benny,
yes.
I mean, when you talk about something like pi-zero mass, then there are combinations even for the measured. I mean.
I may address that question later, but in this particular, let me put it that way. If you plot decaying pi-zero mass, it will be a delta function. If you take the two photons, photon 1 and photon 2, kin fit, and you plot invariant mass, the sum of photon 1 and photon 2, kin fit, invariant mass, you will also get a delta function because it's the same thing as decaying pi-zero. If you take the measured quantity of the photon here, if you take this variable from photon 2 and this variable from photon 1 and plot the invariant mass, you will get the Gaussian distribution that looks like it does not have any background. Okay?
Yeah, all right.
All right. All right, so now if you want to have some code to actually run over or analyze such a root tree, access the data and plot something from that root tree. All the software is related to that is in the package GlueX root analysis, as Mark was already pointing out earlier. And in that package, if you find the home directory where this guy lives in, you will find a subdirectory called bin, where binary, and one of these the three binaries that's in there is called make deselector. And that script will create two files for you. One is called deselect. Well, I should say how you start it. You have the script. You give it an input file that contains the root tree you want to analyze. A second string that specifies the actual root tree name in this file. And a third parameter is a program name of your choice, my analysis, for example. Right? And that will create two files. One is called deselector underscore and the program name you gave it, myfile.h, a header file, and a root C file, a script, macro file. However, the macro or the two files are written together in such a way that you can compile that. We'll talk later. Now, to then use this program, you loop over the root and loop over the root tree and analyze a root tree is shown here. You create a chain with the chain name, the root tree name. You add a file to this chain that contains this root tree. Then you have this magic line here that is part of the groot analysis package. And then you say chain process and your C program that you have created, the two pluses in the back just forces the script to compile the code, even if the objects already have been created earlier. Is that so clear so far? Right? So now, by doing this make deselector, You have created 2 files, and now your work starts. Up to now, you haven't done much, but you have basically created 2 files with some code skeleton in it, and now you have to modify this skeleton according to what you want it to do. The deselector program package library provides methods and wrappers with methods to access the data in the root tree. And as I mentioned earlier, in deselector.doc.pdf, I tried to start compiling a description of how to use the code, what's in there, and what's the best way, describing some of the methods that are in there and the wrappers. And so, for example, your deselector underscore your name inherits methods, and one method is get run number or get event number, and with that you automatically get for each event the numbers out. And then the second part, the more complex part, are the wrappers that refer to particles in your root tree and combos. And the first 3 of these wrappers, think of them like they are arrays, but they are complicated arrays because these arrays also have methods. Because with these methods of the array, you can actually, first of all, set the index or the pointer to the right locations in the array, and then using the methods of these arrays or classes to access the data. And the first 3 are the decharged hypo wrapper, deneutral hypo wrapper, and debeam wrapper. These are related to the measured input quantities that are in the root tree, namely the beam photons that we have, that's the debeam wrapper, all the final state particles you have, that's the pi plus, pi minus, kaon, photons. The charged hypos would be that all charged tracks, and the neutral hypos are all photons or neutrals. Mostly photons could also be neutron, but basically showers that are not related to a track. Right. And then there's a second part of wrappers called decombo wrapper, decombo beam wrapper, and departicle wrapper. By particle, I mean it could be a proton, pi minus, pi plus, decaying pi zero, as you have seen earlier, and so forth. These 3 are related to the actual combos. That's after the kinematic fitter. So now these wrapper combos, these wrappers have methods. And some of the methods are listed here just to give you a basic idea. They're mostly get underscore something. That means you get some data back out of the root tree. And of course, depending on what type of particles or type of the wrapper it is, that they may be completely different, but some of them are also very similar. So you will most likely have an X4 underscore measure for the beam, but also for the neutral and charged particle, because that refers to as the 4-vector position of the measured quantities. Or P4 relates to the momentum of the measured quantities. These give you back actually a T Lorentz vector in the root script. Is that more or less clear so far? Right.
Those are the values you can play with, like when you do analysis.
When you do analysis, I will go more into the specifics. So one point I want to make here, the kinematic fitter only changes the final state particle. That means any positive, negative charge particle or a neutral particle. It will never, ever change the beam photon because that's the input to the kinematic fitter. That's the initial state. The initial state is not varied in the kinematic fitter, only the final state.
Why not?
I think because one of the reasons is I think our resolution of the beam photon is more than good enough to kinematic field.
It's much better than for
Much
the rest.
better than the final state
Okay.
particles, yeah.
Yeah. I hadn't known that.
Yeah. So I mean, in principle, you could put that in there, but because the resolution is so much better, we haven't put in the full.
That the vertex is changed, obviously. Yes. But the energy of the beam photon not, the direction not, and the target not, unless with respect to the position, yes. Okay. All right. Okay, so now remember that this selector underscore your name choice that I mentioned at the beginning. In there, in that code, in the .c file, you have three methods defined. One is called init, one is called process, and one is called finalize. They are basically overriding the methods that were provided by T-selector, because T-selector inherits from T-selector, which is the root libraries. And the init is, contrary to what you would expect, called more than once. It's called basically every time a new file is opened. In T-chain, if you have more than one file, then init is called as many times you have a file. Process, that's called every time you have a new event. And then finalize, that's called one time at the very end. So let's go first to init. In init, that's the location where you define initialize variables at the beginning of analysis and define initialize histograms. But as I mentioned, because init is called more than once, most likely, there is a switch in that code somewhere when you follow through, and you will find this switch, and it will check has this subroutine or this method already been called or not. If it has been called already, then it will return, and whatever follows here will not be executed. So any variable you want to initialize at the very beginning of your analysis, and all histograms that you want to declare has to happen afterwards. Otherwise, you will overwrite it every time you go into this init function. I should mention there are many comments in there that try to explain to you what the code tries to do or is going to do. My coding abilities are limited, so I may understand half of what's written in there at most. You may understand much more than I do. There are comments about cut action, analysis action, histogram action. I don't know anything about that. That's why I will not talk about it. So that's where you guys come in. If you ever find out how one of those things work, please go to that overleaf documentation and write in what you know about it. But for what I'm talking about and what I try to show you is that to some degree you don't need this if you want to do an analysis on your own. But in particular, I think cut action may be a useful tool to give you additional ideas and overviews of what's going on in your event selection. Now, the main part of the code where you do your analysis is in the method process. And the argument it gets is a long int, and that just represents the event number, so to speak. Notice I used an I removed lock something. So for example, you can ask, how did I do that? Maybe okay, I get a little bit confused. But there is somewhere a line in yes, there is actually very soon after process and some comments, there is this line, deselect colon process I. Remember, you see there is no underscore my code. So this is actually the call, the process method that is inherited from tselect from CERN. And that loads the actual data into memory that you then later on can access, as I will show on. But when you then ask get event number and you look compare event number with this I, you will see that the I's, that the event number is not consecutive, but I is. So if you would print I and event number, then I would nicely increment 1, 2, 3, 4, 5, 6, 7, blah, 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 whereas event number could be quite random. The reason for that is we analyze we generate the REST files in multi-threaded mode. So when that gets written into your REST file, data file, the events will not show up in consecutive order. They will show up in an order which event has been analyzed faster than the next one. All right. So now in there at some point, you then get to where you loop over the combos. And again, there's a comment there that probably will tell you, and this loop will look something like that, where you have a counter that loops over the number of combos of a given event. And the first thing it does here is the decombo wrapper, it sets the combo index to the counter number. And that command will make sure that all the pointers in this event are set to the correct index for your wrapper functions with which you access all the data. All right. Now, so for example, instead of looping over combos, you could loop over the number of charged tracks you have in your root tree for a given event. That you could do, for example, with something like that. Again, you get the number of charged hypos, and then you have to set the pointer for the, remember this, I said this is an array, but it's more than that, it has methods. And one of the first things you have to do is you have to set the index of this array to the proper location so that you can access the data, and that is done by set array index. Right. And then from that on, you can use all those methods to access the data that is associated with these charged particles. Okay, then at the end, finalize. You write out all your stuff, you save all the stuff you created. You may have opened the file and added some additional stuff in there. And once that is done, at the very, very end, deselect the finalize is called, and that will then write out all the histograms you have created into a predefined file that you have specified at the beginning in init. So I want to go just a little bit closer to to the question of what constitutes a combo. I mentioned it earlier already, but I want to just drive this home a little bit more so that it becomes clear and doesn't produce any confusion. So all final states plus one beam photon plus the target constitutes a combination, a possible combination that when you give it to the kinematic fitter, the kinematic fitter will not barf and will actually give you a reasonable result. And the combinations that you can have for a given event is for each beam photon you have a combination. For each final state photon you have a possible addition. Sorry, for each additional final state photon you can have a combination that comes into place with the term unused energy that you have in your thing. So for example, if you have 3 photons in the final state, but you only need 2 to make the pi 0, then that third photon is unused energy, which means for each combo, the unused energy is different because you used a different photon. Similar, each additional charged track can make you a combo. So if I have more than one negative charge track, then I have already more than one combo, right? What's important is the combo is in the in the root tree only if the kinematic filter converges.
Is that actually true?
Yeah, because if it doesn't converge, you do not have a chi-square.
Yeah, because I thought I saw now indication that in the tree, within an event, one combo survived the kinematic fit, the entire event gets copied over into the tree. Likewise, that's why I noticed at first when you clone a tree and put cuts on there, as long as one combo within the event fulfills your whatever cuts you put on, and you clone the tree, the entire event with all the combos that don't fulfill that also get into the clone tree. And I thought I saw also that if you look at the first tree that gets generated of the reaction filter, that the entire event gets copied over if at least one combo survives whatever cuts are in the reaction filter.
So only tracks that are used in a combo are saved to the tree. So there could have been 5 tracks, and if only one combo passed the kinfit confidence level, you'll only save the tracks from the event that are used in that combo. So not all of the unused tracks in the event are stored to the tree by default. You can set a flag, the -u flag that Alex was talking about, which says save every track into the tree. But by default, you only save tracks that are used in a combo.
In some combo.
Some combo that has a kinematic fit confidence level.
Okay, okay, no, I understand. So the combo, I see other combos, it's still in there, that might not have passed the kinematic fit cut, but they're using the same tracks as the one combo that has passed it.
No, I think so. Benny's statement here is true, that there's only combo data stored for combinations that pass the kinematic fit confidence level cut. So if there's a track in the T tree, it must have been used in some combo that passed the kinematic fit confidence level cut.
Well, it just has to converge, right?
It just has to converge. Yes, that's right. So if there's a track in our default T tree, that means it exists in one of the combos that has a confidence level or a kinfit that converged.
Is this a stage that is defined in the filter, or is it like the user-defined analysis? Like, will have converged like when processing the rest file, or deselector editing?
The requirement of convergence is when the reaction filter runs.
Yeah.
Then you can apply tighter requirements on the confidence level later on.
I think Dr. Reinhold was asking more so about tighter cuts, right?
I was asking what was in the tree.
Yeah. So, but then when you go and
cloning the trees.
When you clone the tree and you make another copy of it that makes a tighter requirement, then you can choose which combos get written into the new tree. And it will make a copy of the whole event, but you can choose that only the combos that pass your cut are saved. And so you might save the track itself into the tree for further processing, but you can require only the combos that pass your cuts make it in. So the whole event might be there, but you can specify which combos in that event you want to analyze later.
Now I realize I misunderstood you a little bit. When I say this, what I mean by that is that the reaction filter that was run to produce the rest file you will have combos in your list that where the kinematic filter converged. It will not write in a combo that did not converge. But you're right, using the D reaction filter, you run, using the deselector over your data, and at the end you say, one combo survived, write out that event, then it will write out all combos, not just the one that survived.
But you can set it with the flag so that when you analyze that tree later, you only analyze the combos that survived.
So there's code.
Yeah, that's the is
Right,
combo cut.
right.
His combo
His
cut
combo
is
cut,
the flag.
correct.
Flag, yeah.
So the whole event
yeah.
will exist, but you will only see the one that has that
yeah,
flag set.
Right,
If you use
That is actually a line. Well, it doesn't really matter, but I think it's somewhere here when you look in your pre-made deselector file. There is somewhere in this loop there is a statement saying is combo cut. And if that is true, return.
Right.
Or continue. I think it's sorry, not return. Continue.
5 minutes left.
Oh, okay. Right. We should. All right. So I thought I give a little example of just rough what you already will see in your skeleton file, so to speak. But look again at this reaction with 3 pions in the final state. Then this is the important line here after you are in the loop. The first thing you have to do is you have to set all your pointers to the right place. That is done by combo wrapper set combo index. That will set all the necessary pointers for all other combo wrappers, or for all other wrappers to the correct values. So I show here now I get the combo beam wrapper because even though the beam photon does not change in the combo by the kinematic fitter, it will create a pointer to get the momentum. I get the pi plus, pi minus, and the proton, and I get a decaying pi zero because the mass has been constrained, but the pi zero decays into these 2 photons. I use get underscore P4, that means I get the Lorentz vector for all these particles. And then, so here, let me go back down here. Then I can, for example, calculate the invariant mass, or the 4 vector of the 3 pion system in the final state, and I can fill a histogram with the invariant mass of that system. Back. I can also get the RF time of the event and the vertex and position, and then I can calculate where the event happened in the target, because the vertex. The vertex minus the flight time of the photon will give you the position along the target. And then you can fill this value into a histogram again. I will come to this histogram in a second, I guess. Yes, I want to show it here again, because when you do that and fill it in, you get this histogram you have seen already many times. And with this, I should have said I come to the last slide, because what I want to talk about shortly is the accidental subtraction. So the big peak in the middle, that's from caused by beam photons that are in time in your reaction. But you see these peaks on the side, these are accidental photons, additional beam photons that the tagger registered, and that also generated where the kinematic fitter found a solution to it. But the beam photon is out of time. And you know that you have about this much background underneath this peak, and then one way to subtract the background underneath here is by taking events from here and subtract it. And an easy way to do that is you create a weight of 1, and you say if the time is outside of these 2 nanos plus minus 2 nanoseconds, go back, outside of these 2 nanoseconds, then you set it a negative weight with the number of bunches you wanted to consider. In this particular case, it would be 8, right? And then you fill the histogram with your value you want plus the weight, and that automatically takes care of everything and will subtract the correct amount.
That's something I know. I noticed that our folks here for you were starting to do that, and that's something that I find. I'm not sure I agree with the method of doing this. I would say that the best way to do is fill them in 2 different histograms so that you actually see how your background looks like.
Yes, you can do that too, and it has been shown that it is exactly the same. And more important,
statistically, it should be the same.
It should, I agree with you. It should be the same, but is it the same? Yeah. You have to convince yourself. What more importantly, and that's what Rich pointed out. What's also important is that when you do it this way, the errors are taken care of correctly.
Yeah. So there's one case that we just stumbled across where this is not the case. This is when your signal is low statistics and you have bins that are not filled, and you subtract, let's say a minus 1/8 of it with a very small error bar. It doesn't do the error correctly if the statistics of your signal is small, right. Especially if it's 0. You get negative numbers which are unphysical at that point.
That is
with unphysical error bars.
That is correct. Yes. Right. Yeah. There's some additional issues I wanted to. Okay. So I should mention that because these values are usually then you fill in say kinematic fit variables, right? But you could in principle also use measured values. However, there is a problem or an issue, potential issue with that, because for each combo, right, the kinematic fitter will modify the measured quantities of the final state particles to make the fit converge. That means the kinematic fit quantities will be different for different combos, but the measured quantities not. In other words, if you have a combo where you have always the same recalled proton, just the pions change, the measured value of that recalled proton will not change, obviously, right? So if you fill a histogram with that quantity of the proton measured quantity, you will fill, and you have 3 combos that survived, you will fill in 3 times the same thing. Or you will subtract at that point at the same place where you filled it in, right? Whereas when you use the kinematic fit value, the kinematic fit value will be slightly different for each call to fill, right? So in this case, and for your example, if you would use here the measured value, then you would not get a negative number by accident.
You still could.
Forget.
So that last line.
Most likely not. No, you would not.
No, you could.
You could potentially, yes. You could, yes.
So you're telling it to fill. So where read it's like you're filling background.
No, here you fill for a given value with the weight. If the weight was 1, it's 1. If the weight was if the event was made with a beam photon for here, it will have a weight of -1 divided by 8.
Yeah.
If the beam photon was here, it was filled with 1.
Okay.
What do I want to say here? Yeah, that's just the same thing as I wanted to say previously. That's it.
Okay, thanks, Vinny. So we had a lot of questions, maybe a couple more, Dave?
Maybe just one quick question. I was looking for slide 6.5 where stop talking about combos said there's a trigger, and then you do the kid fit, and for the reaction of interest, probably the things we want usually survive the kid fit. Then you can look at a bunch of combos, but you'd like to come out, in most analyses, you'd like to come out with one.
All right. Okay. So
And
now
then you sort of went into accidental subtractions, and I don't want to do accidental subtractions for 15 combos.
yeah, but most of those 15 combos may not survive your confidence level cut.
That's
Right.
where I'm looking for slide 6.5, where you apply that.
Okay.
And get
I
on
have
with
not.
your life.
I was considering that as trivial.
Okay, right.
Sorry.
It can't be too trivial for me.
Did I write that down somewhere? I did not. Because I did a test. You can have combos where the confidence level is 0, literally 0. The reason is, but chi-square will be not 0. But because the confidence level is a calculated number based on the degrees of freedom and the chi-square, you can have a number that becomes too small, and the float or double float or whatever is used to store that value cannot handle it and will just be 0.
Yeah, I don't work down. Anything below 10 and minus 5 is probably
Right.
not interesting.
Right, but I thought you would go for another thing is you can potentially have two, particularly when you have more than one charged track, additional charged track, or an additional photon, where the kinematic fitter with the beam photon, the same beam photon, will give you a good solution. And both are above a certain confidence level. That means you would have for one event 2 times filling in a histogram with weight 1. And that is an issue of uniqueness, and I didn't want to address that because it hasn't been properly addressed at all yet by us. And that is one thing that should be on top of our list at some point and discuss about what's the best way to handle that.
Yeah, well, if it's of order 5% as it was in the J-Stein,
Correct.
where they used a very low.
It depends obviously
Cutoff, then
on
it's
your
not
reaction.
such a big deal.
Right, it's not a big deal, but there could be other reactions where it potentially is. I could imagine where you have a lot of photons, it may potentially cause an issue.
Okay, so thanks, Benny. I think we need to move on. Matt is now going to tell us about a different style of data analysis.
I'm going to try to share the screen. Is that okay?